Inside a modern multi-core chip, millions of operations execute across a microscopic lattice every second. It is a dense, highly coordinated environment where hardware designers divide workloads across multiple processing centers to accelerate execution. To quantify how well this works, engineers use a simple primary metric, parallel speedup. This is defined as the time it takes a single processor to execute a program, divided by the time it takes n processors to execute that exact same program. Look at that fraction, and a highly intuitive assumption emerges. If you double the number of cores, you should cut the execution time in half, yielding a one-to-one improvement in performance. That assumption collapses when we look at real-world benchmarks. Researchers often fall into the superlinear trap, reporting performance gains that exceed the physical capacity of their hardware, simply because they are measuring against an unoptimized sequential baseline. This schematic illustrates the scale of the environment we have to measure. Evaluating parallel performance means tracking data from localized hardware components out to sprawling cloud infrastructure and external databases. True system evaluation happens across 3 tiers. We must analyze the algorithmic data flow, scale up to the program logic, and finally map the physical queuing physics of the entire network. We start at the micro level. Here, we examine individual CPU cycles and apply the fairness rule of algorithmic baselines. Before we can determine how fast a parallel system operates, we have to prove exactly how slow the most efficient sequential version of that task actually is. Consider a standard 4th-degree polynomial equation. This provides a clear test case to measure performance at the instruction level. This data flow graph maps the equation for a single processor. Counting the nodes shows that the hardware must execute exactly 11 operations, combinations of multiplications and additions, to reach a result. Assuming 1 cycle per operation without pipelining, that takes 11 cycles. When we look at this next graph mapping the same equation across 3 processors, the workload is distributed. The horizontal dotted lines show that by running operations simultaneously, the total execution time compresses down to exactly 5 cycles. Using our basic formula, we divide the original 11 cycles by the new 5 cycles. That gives us a calculated parallel speedup of 2.2. But we need to verify the baseline. In computer science, Horner's method is used to evaluate polynomials because it minimizes the total number of mathematical operations by factoring the equation. This revised data flow using Horner's method shows a much leaner sequence. By applying this algorithm, the total operations required to solve the exact same equation drop from 11 down to exactly 9. Because we have a more efficient 9-operational sequential baseline, the initial single processor metric of 11 is invalid. We have to recalculate our speedup against this optimized algorithm. We take the true baseline of 9 operations and divide it by our 5-cycle parallel time. The actual parallel speedup is 1.8. By using an unoptimized 11-operation baseline, the initial test created an illusion of 22% more efficiency. The hardware didn't do the work faster, the sequential test was just poorly written. This illustrates the rule of fairness. Benchmarking a parallel system requires using the best-known sequential algorithm for that specific task. Claims of superlinear speedup, where the performance multiplier exceeds the number of processors, are usually a sign of an intentionally weak sequential baseline. Scaling up from individual CPU cycles, we look at the entire codebase of a program. At this macro tier, performance is constrained by the serial fraction, the percentage of code that cannot be run in parallel. To predict maximum speedups when the workload size is fixed, we use Amdahl's law. Imagine you optimize a program. You rewrite 40% of the code to run 2.3 times faster on parallel hardware. The overall system speedup will be significantly lower than 2.3. The remaining 60% of the code is unchanged, forcing the processors to wait in a single file line while that serial logic executes. Amdahl's formula dictates a strict ceiling. Because 60% of the program is serial, even with an infinite number of processors, the speedup for this specific program can never exceed 1.667. Gustafson's law offers a more optimistic view. It assumes that as engineers add more computing power, they also increase the problem size to fully utilize the new hardware. Gustafson expresses this as speedup equals n minus alpha times n minus 1, where n is the number of processors and alpha is the serial fraction. If we apply this to a system with 32 processors and a serial part of just 3%, the math yields a speedup of 31.07. Amdahl's law shows when it becomes useless to throw more hardware at a fixed task. Gustafson's law shows how much additional work can be completed once that hardware is installed. The scaling potential of a system is governed by the serialness of the logic, independent of the total core count. At the largest scale, we look at steady-state networks like parallel web servers and database clusters. Here, data flow behaves according to queuing physics. The movement of items through any steady-state system is governed by Little's law. The formula states that L equals lambda multiplied by W. L is the average number of items in the system. Lambda is the arrival rate. W is the average time an item spends being processed. Consider a parallel web server receiving 1,000 requests per second. At any given moment, there are exactly 150 requests currently being processed inside the server. We divide the 150 items in the system by the arrival rate of 1,000 requests per second. The math reveals an average latency per request of 150 milliseconds. Now consider a computing cluster completing 90 jobs per minute, where each job requires an average of 4 minutes inside the system to finish. Multiplying the arrival rate of 90 jobs per minute by the 4 minutes of wait time reveals that the cluster is sustaining 360 concurrent jobs. These variables are mathematically linked. Increasing the volume of tasks entering a system without speeding up the processing time causes the number of tasks in progress to rise, which lengthens the queues. This applies directly to multi-core CPUs. Allowing more instructions to enter the execution pipeline necessitates higher total throughput to maintain low latency. Little's law proves that increases in work in progress are a mathematical tax on completion time. Performance evaluation happens across 3 distinct layers. We start at the gate and move out to the global network. At the micro tier, speedup depends on an optimized sequential baseline, such as Horner's 9-operation model. At the macro tier, scaling software involves balancing Amdahl's serial bottlenecks against Gustafson's workload expansion. At the system tier, latency is a consequence of arrival rates and processing capacity, governed by Little's law. These 3 formulas provide the mathematical framework for measuring parallel systems from the processor level to the network edge. Adding hardware is a capital expense. Measuring and verifying hardware is operating at its maximum theoretical efficiency is the mark of rigorous computer engineering. Speedup is a numerical result of a calculation. Efficiency is a property of the architecture.